So in this lesson, we're going to start our study of Riemann sum, summation notation, and definite integral notation. So we are bringing back the idea of the sigma notation. We are not doing series yet. That's coming, okay? But we're going to learn at least, talk a little bit about some basic series stuff. And we're going to use the limiting process to find the limit of a definite integral. And you're going to be able to use that limit process to find the limit of a definite integral. And I'm bringing this lesson in because number one, it's part of our course description. It's something that we skipped. It also helps us bring back this sigma notation before we actually have to reintroduce it again when we do Unit 10. So we're going to talk about sigma notation and what that really means. So basically this is it's a sigma symbol and it means sum. Okay, so it stands for sum, much like the integral stands for sum. And there's always an index, and this is basically our term numbers. So this is the term numbers. And we would have to substitute those term numbers into whatever function we're given. It gives us a lower bound, much like a lower bound of an integral, and gives us an upper bound. So you can see that what I did was I plugged in a 1, and then I plugged in a 2, and then I plugged in a 3 until I got to that upper bound of n. So basically what that means is we're going to add up all those terms that we created in our series. So I'm going to start by plugging in a 1, and then I'm going to plug in a 2, and I'm going to plug in a 3 because all of my function is just I. Plug in a 4, plug in a 5, and plug in a 6. And I happens to just stand for the word index. It could be a J, it could be a K, sometimes it's an N, all right? And then when I add these up, I end up with 21 on this one. Now, I could do a calculator on this other one, but I'm just going to go ahead and do it by hand. So I know that I'm starting at 3 this time, and I'm substituting it in. So I've got 9. I'm going to square it in my head. So 9, 16, 25, 36, 49, because I'm putting up the 7 there. I'm putting an 8 in, 64, put a 9 in, 81, put a 10 in, 100, 11, 121, and 12, 144. So when I add all of those up, I would get 645. So just like limits, just like derivatives, just like the integrals also have, or the summation properties also have some properties and formulas just that are true about them. If I have a constant on the inside, I'm allowed to bring it outside. That's a big one. We're going to use that today. I'm allowed to break them into two summations with when there's addition or subtraction. Okay, so I can use that. So you can break it into two separate things. So the following formulas will be very useful when evaluating summations with larger upper bounds without a calculator. So if I just have a constant from 1 to n, it's just the constant times n. If I have 1 to I can use this formula. And actually, this guy over here, this Carl Friedrich Gauss, he's the guy that actually invented that formula at the ripe age of 5. So his teacher thought he was being funny, or the good old Carl was bugging the teacher, right? So the teacher thought, hey, I think I need this kid to take a while to do something. So he's like, add up the numbers 1 to 100. And back in those days, no calculator, he had to do it by hand, right? Well, he stumbled upon this pattern of this formula and came back just a few minutes later and solved it. So that's what he's renowned for. So he's renowned for this formula right here. I squared is this formula, and I cubed is this formula. So we're just going to take those as truth. When I see the summation of I squared, I'm plopping this in. When I see the summation of I'm plopping this in. When I see I cubed, I'm plopping that in. It's a good way to convert it from i's into n's for our purposes. All right, so we are supposed to evaluate the following summation. So all I'm going to do is take those formulas that I had on the other page, and I'm going to substitute them in, okay? So, and I know I'm going from 1 to 10 this time. So I am going to plop in the I squared, which I know is this guy right here. So I am putting in n times n plus 1 times 2n plus 1 divided by 6. And again, that replaces the entire I squared. Then I'm going to subtract the I, which is n times n plus 1 over 2. And then the last part is just plus 4. So, and we need to evaluate that for n equal to 10. So that means I'm basically going to plug a 10 into all of those. So I've got 10 times 10 plus 1, which is 11, times 2 times 10 plus 1, which would be 21, all over 6, minus 10 times n plus 1, which is 11, over 2, plus 4. Let's see, 6 goes into, what's 6, 2, and so I got 5 and 3 left over, right? 3 goes into 21 7 times. So we've got 5 times 11 times 7, which would be 385. 2 goes into 10 5 times, so minus 55 plus 4. So that summation ends up being 370. Now comes the part that we probably don't want to revisit, but we're going to revisit writing this in sigma notation, okay? So that basically means I need to figure out the pattern, okay? What is creating this sum from, and you can use just I equals 1, and we know we've got, well, we don't know how many terms yet. So I'm looking for the pattern. I notice that that's not what I wanted. I notice that this is identical in all the terms. So I know that that has to be in every single thing I do. So I'm going to do 5 over 1 plus. Then I need something that represents the term number. So this is my first term, second term, third term. So and my formula is always based on the term number. And we can put that term number in terms of I. So I noticed that, hey, that matches the term number exactly. So I'm just going to put an I right here. And I also noticed that this last one that I've got, this is finite, it stops at 15. So my upper bound should be 15, and that gives me my summation formula there. Now this one, believe it or not, I think it might be nicer. So I equals 1. And I'm noticing, okay, I'm looking for a pattern. I see that this is different, and this is different, and this is different. And hey, what do you know? Look at that. They gave me the formula. Wasn't that nice of them? Instead of ends, though, the only thing that's actually changing, on the part that's actually changing, this part here, I'm going to plop in an I. Okay? So really think about what was happening. If this is term 1, I'm doing 2 times 1. If this is term 2, I'm doing 2 times 2. If this is term 3, I'm doing 2 times 3, which is where the 2n is coming from. So we're going to do 1 minus parentheses 2i over n minus 1 squared times 2 over n. And this is going to go all the way to the nth or nth end.